Welcome to this workshop on adding PIDPlus to legacy control systems. In this video, we will examine the solution to the workshop contained in Chapter 10 of the book Wireless Control Foundation. In this workshop, we'll be showing a number of exercises that are used to show how PIDPlus can be added to any legacy control system using the tools that you find within the control system. In the first part of this exercise, we'll look at a module that contains our traditional PID for single loop control. We'll then identify the composites that are needed to be added to the control module to provide PIDPlus capability. We'll then examine some composite blocks that are used to simulate the process so that we can test this. And then we'll enable wireless control and introduce both set point and disturbance changes to demonstrate the control using PIDPlus implemented in this way. Here is the module that we'll be using. As you notice, we have an input-output and a traditional PID in the control module. The input, though, in this case is being provided by a wireless transmitter. We're simulating that wireless measurement to demonstrate wireless control. The PID in this case is set up where there's a parameter called dynamic reset limiting, which is used to enable external reset. And so in this case we've enabled external reset, and the input coming in on back cal in then is used in the positive feedback network that is used to calculate the reset component. The implementation of PIDPlus are two composites. The first is used to just detect a change in the wireless measurement, and so you see here that we're providing an output of 0, 1 based upon whether a new measurement has been received. That new flag measurement is then used in a second composite that is acting upon the normal input that would be provided to the back cal in. When wireless is enabled, then we are going to be doing a calculation of the filter in the positive feedback network. In the first part of this calculation, we'll be looking at whether wireless is enabled. If it is, then the reset of the PID is set to 0. If it is not enabled, then the normal reset is in the PID. When wireless is enabled, then we'll be calculating a filter, and that will be based upon the reset time. And when we get a new measurement, then we will actually use the filter output as the value provided in the positive feedback network. Otherwise, it is maintained at its last value. And so you see the implementation of this calculation is quite straightforward and can be implemented on most DCS systems. The combination of these two composites provide us our value that we're going to use in our positive feedback network that creates the reset. To demonstrate this capability, we've created a process simulation, and you notice that in the process simulation, the process has a dead time of 2 seconds, a gain of 1, and a response time of 6 seconds. And so our reset then is set to 8, that is the time constant of our process plus the dead time, and the gain is set to 1. So we're tuning the control for a lambda factor of 1. The communication is window communication with a deadband of 1%, a period of 16, and a default time of 32 seconds. Here we've enabled online operation then of this module with the simulation. In this particular case then we have the PID initially set up where the PID mode is set to manual, and so it's just maintaining its output. If we examine then the PID, its reset is 8 seconds, so that is the tuning of it. When we enable, though, wireless control. That is, we're enabling the composite now to be doing its calculation of the filter. The reset of the PID is automatically set to 0, and the calculation of our filter is then based upon the reset which has been captured within the composite. So it's using the 8-second reset time in its filter calculation. And so that then is being used. So to demonstrate this capability, we'll turn our PID to automatic control, and we'll introduce a 10% set point change. So as we introduce the set point change, you notice that the output of our PID immediately responds to that set point change. That change in valve position then is impacting our measurement, but we don't see that immediately due to the window communication. So that's only being updated every 16 seconds. When we look at the trend, then we notice that the valve changes for a set point change, but our measurement only changes every 16 seconds for a large change in measurement. And once the measurement gets close to our set point, within 1%, then the actual value is only updated every 32 seconds. And so when the change in value is less than 1%, then we only update and communicate the new value every 32 seconds. When we do get a new communication, you notice we're very close to set point here. And then over time we get exactly to set point using window communications. To demonstrate the response for a disturbance change, we'll introduce a 10% disturbance into our process simulation. In response to that disturbance, our process starts to immediately respond, but we don't see that response immediately due to the window communication. And so only when we see the new measurement do we then sense that a disturbance has occurred. And but when we do sense the disturbance has occurred, then we take immediate response in our PID. And again, we're only updating every 16 seconds with our window communication. And once the response starts to only change by less than 1%, then we only update every 32 seconds. But as you can see here, we've very quickly responded to our disturbance, and very quickly have corrected for that, and have brought our control parameter back to set point. In the windowed communication, then we only update every 16 seconds. If we're within 1%, we only update every 32 seconds. And so with window communication, you're using very few new measurement updates, and yet you notice we're able to do a very effective job both on set point change and disturbance change in terms of control performance. So we hope this demonstration has been helpful in terms of you seeing how it is possible in a traditional control system to implement PIDPlus. Basically, we implemented two composites and used the capability of the PID to support external reset. So as long as your PID supports external reset, you can build the filter outside of the PID. You can then use the normal reset in the filtered calculation. In implementing this, it's important to train an instrument technician the fact that the PID reset will be set to 0, and that tuning of his control is set through this composite. The tuning is only based upon the process dynamics and is totally independent of the update and sample time, as has been demonstrated in this workshop.